What if everything you think you know about temperature is just the tip of the cosmic iceberg? Picture the universe not as a static, predictable place, but as a dynamic arena where heat and cold wage an eternal battle. From the unimaginable fury of colliding stars to the eerie stillness of empty space, where temperatures plunge to depths colder than anything we can create on Earth. This isn't just science, it's a story written in the language of energy, a tale that stretches from the first moments of creation to the far future of everything. And today, we're going to unravel 24 of the most mind-bending theories about the universe's temperature, each one a puzzle piece in the grand mystery of existence. Think about the last time you felt truly cold. Maybe it was a winter night, or the shock of stepping into an air-conditioned room. Now imagine a cold so profound it defies logic. Patches of space where the temperature hovers just above absolute zero, the point where atoms nearly stop moving entirely. These cosmic cold spots aren't just curiosities, they're clues to the universe's hidden structure, whispers from the void that challenge our most fundamental ideas about energy and matter. On the other end of the spectrum, there are places where heat reaches levels so extreme they warp the fabric of reality itself. Black holes shredding stars into superheated plasma, or the afterglow of the Big Bang still echoing across the cosmos. How can one universe contain such extremes, and what do they tell us about the forces shaping everything we see? This journey isn't just about numbers on a thermometer. It's about the stories behind them, the brilliant minds who dared to question the impossible, the experiments that revealed truths stranger than fiction, and the mysteries that still keep scientists awake at night. We'll explore why some regions of space refuse to warm up, how dark matter might be silently dictating the universe's thermal map, and whether the very concept of temperature could mean something entirely different in the depths of a black hole. By the time we're done, you'll see the cosmos in a whole new light, not just as a collection of stars and planets, but as a living, breathing entity with its own pulse of heat and cold. So buckle up, we're about to dive into the thermal secrets of the universe, and trust me, nothing will ever feel the same again. The Big Bang wasn't just an explosion, it was the birth of heat itself. In that first fraction of a second, the universe was a seething ocean of energy, hotter than the core of any star. But as space expanded, that heat stretched and cooled, leaving behind a ghostly fingerprint, the cosmic microwave background. Imagine it as the universe's first photograph, taken when everything was just a toddler at 380,000 years old. This faint glow isn't just radiation. It's a time capsule carrying secrets about how matter clumped together to form galaxies, why some regions of space are eerily empty, and even whether parallel universes might have brushed against our own. Yet here's the puzzle. If the Big Bang was a uniform fireball, why does this background radiation have tiny temperature fluctuations like a patchwork quilt of hot and cold spots? Some areas are just a fraction of a degree warmer than others, but these imperfections are cosmic gold. They might hold clues to forces we've never seen, like dark energy's grip on the universe's expansion, or the echoes of violent collisions between dimensions in the earliest moments of time. Picture space as a canvas, and these temperature variations as brushstrokes left by invisible hands. And then there's the cold spot, an anomaly so bizarre it defies easy explanation. Stretching over 1 billion light-years, this region is strangely cooler than its surroundings, as if a piece of the universe forgot to warm up. Some theorists whisper it could be a cosmic bruise, left by a collision with another universe in the multiverse. Others suggest it's a vast void where dark energy behaves differently, warping the fabric of reality itself. Whatever the truth, these thermal fingerprints prove one thing: the universe's birth wasn't tidy. It was chaotic, uneven, and far more mysterious than we ever imagined. What's even wilder, this background glow is slowly fading. Over trillions of years, it will dim to near darkness, leaving future civilizations with no obvious trace of the Big Bang. We're living in a privileged sliver of time, able to glimpse the universe's fiery origins before the evidence vanishes forever. So when you hear static on an old radio, remember, about 1% of that noise is the dying whisper of creation, a reminder that heat isn't just a measurement, it's the universe telling its story. Those tiny ripples in the cosmic microwave background, each no larger than 100,000th of a degree, are like cosmic breadcrumbs leading us back to the universe's infancy. Picture the early cosmos as a simmering soup of particles, where denser regions pulled in more matter through gravity, eventually growing into the galaxies and galaxy clusters we observe today. But here's where it gets strange. These temperature variations don't quite match what our best models predict. Some patches are too cold, others too smooth, as if the universe played by different rules in its earliest moments. Take the so-called axis of evil, an eerie alignment of temperature patterns that seems to defy the principle of cosmic randomness. If the Big Bang's aftermath was truly chaotic, why would these fluctuations line up along a specific direction, almost like a fingerprint smudged by an unseen hand? Some theorists suggest this could be evidence of a pre-Big Bang structure, a relic from a time before time, while others propose our entire observable universe might be caught in a gravitational wake left by something far larger lurking beyond our view. Then there's the cold spot, a sprawling region of space where temperatures dip lower than standard physics can explain. One compelling theory: this might be the imprint of a cosmic texture, a defect in spacetime itself, formed when fundamental forces froze into place during the universe's rapid cooling. Think of it like ice cracking on a pond, leaving behind fractures in reality. Alternatively, it could be a window into the multiverse, where our universe once brushed against another, leaving behind a chill no single Big Bang can account for. What makes these thermal mysteries so tantalizing is their defiance. They resist tidy explanations, forcing scientists to question whether dark energy evolves over time, if gravity behaves differently at cosmic scales, or even whether light itself may have properties we've yet to uncover. Every anomaly is a crack in our understanding, and through those cracks we catch glimpses of deeper truths, or perhaps deeper questions. The cosmic microwave background isn't just a snapshot of the past, it's a mirror reflecting how much we still don't know about the universe's fiery birth and its icy echoes. Dark energy isn't just stretching the cosmos, it's draining its warmth. Imagine the universe as a balloon inflating at an ever-increasing speed. Every galaxy, every particle, even the fabric of space itself is being pulled apart. But here's the chilling twist. As space expands, the energy within it doesn't just spread out, it weakens. Photons traveling across the void lose momentum, their wavelengths stretching into colder, redder light. Over billions of years, this relentless expansion could turn the universe into a vast, frigid wasteland, where stars burn out, black holes evaporate, and even the background glow of the Big Bang fades into nothingness. This is the Big Freeze, a future so cold it makes the deepest reaches of space today feel like a summer afternoon. But why does dark energy have this effect? Think of it like a cosmic game of tug-of-war. In the early universe, gravity was the dominant force, pulling matter together and generating heat through collisions and compression. Now dark energy has taken the lead, pushing everything apart with a force that grows stronger as space expands. The farther apart particles get, the fewer chances they have to interact, and without those interactions, heat dissipates into the void. It's as if the universe is running on an ever-dwindling battery, its energy slowly leaking into the emptiness. What's even stranger is that dark energy might not be constant. Some theories suggest it could evolve over time, growing stronger or weaker in ways we don't yet understand. If it strengthens, the big freeze could arrive sooner than predicted, with galaxies vanishing over the cosmic horizon, their light stretched beyond detection. If it weakens, gravity might regain the upper hand, pulling the universe back into a fiery collapse. A big crunch, but for now, the evidence points to a colder fate. The universe's temperature has already dropped dramatically since its fiery birth, and dark energy seems determined to keep turning down the thermostat. Yet there's a tantalizing paradox here. While dark energy cools the cosmos on large scales, it also creates isolated pockets of extreme heat. As galaxies are torn apart, their gas clouds collide, sparking bursts of star formation and superheated plasma. In a way, dark energy is both the architect of the Big Freeze and the cause of fleeting cosmic firestorms, a reminder that even in the grand story of cooling, there are moments of violent warmth. The real mystery isn't just how cold the universe will get, but what happens when temperatures near absolute zero. Quantum physics suggests that even in total cold, space isn't truly empty. Virtual particles flicker in and out of existence, and the vacuum itself hums with faint energy. Could dark energy somehow interact with these quantum fluctuations, rewriting the rules of heat and cold in ways we can't yet imagine? The answers might lie in the next generation of telescopes, designed to map the universe's expansion with unprecedented precision. Until then, one thing is clear. Dark energy isn't just shaping the cosmos, it's slowly stealing its heat. Black holes aren't just cosmic vacuum cleaners, they're also among the universe's most baffling radiators. At first glance, the idea seems absurd. How can an object so dense that not even light can escape somehow leak energy? The answer lies in one of Stephen Hawking's most brilliant insights. Black holes glow, not with the fiery light of stars, but with a faint, eerie shimmer known as Hawking radiation. This isn't heat in the traditional sense. It's a quantum whisper, a trick of the universe where empty space isn't empty at all. Picture the edge of a black hole, where gravity warps spacetime into a steep cliff. According to quantum theory, pairs of particles and antiparticles constantly flicker in and out of existence, borrowing energy from the universe before annihilating and paying it back. But near the event horizon, something extraordinary happens. One particle gets sucked into the black hole while the other escapes, stealing a tiny bit of the hole's energy in the process. Over eons, this slow leak causes the black hole to evaporate, fading away like a snowball in the sun. The colder the black hole, the faster it vanishes, a cosmic irony where the darkest objects in existence are slowly undone by their own faint glow. But here's where it gets stranger. Hawking radiation implies black holes have temperature, a concept that defies classical physics. A stellar mass black hole might be colder than the cosmic background, barely a fraction of a degree above absolute zero, while a microscopic one could be hotter than a supernova. This thermal fingerprint bridges two seemingly incompatible worlds: Einstein's relativity, which governs gravity and spacetime, and quantum mechanics, which dances with particles and probabilities. The fact that black holes obey thermodynamic laws suggests something profound, that gravity, entropy, and quantum weirdness might all be threads of the same cosmic tapestry. Yet mysteries remain. If black holes radiate, where does the information about what fell into them go? Quantum physics says information can't be destroyed, but Hawking's original calculations suggested it vanishes forever. This information paradox has sparked decades of debate, with some theorists proposing holographic universes and others suggesting black holes might leave behind faint echoes of their meals encoded in their radiation. One thing's certain, black holes aren't just celestial graves. They're laboratories testing the limits of our understanding and hinting at a deeper reality where heat, gravity, and quantum uncertainty collide. The real revelation, Hawking radiation isn't just a quirk of black holes, it's a universal phenomenon. Any object with an event horizon, even an artificial one created in a lab, should emit this ghostly glow. That means the universe might be filled with invisible, evaporating remnants of black holes from the earliest moments of time, their final bursts of radiation flickering like dying embers. And if we could detect them, they might reveal secrets about the birth of the cosmos, the nature of dark matter, or even the possibility of extra dimensions. Black holes, it turns out, aren't just cold voids. They're cosmic puzzles radiating questions as much as heat. Neutrinos are the universe's quietest thieves, slipping through matter like shadows and stealing heat right under our noses. Every second, trillions of these ghostly particles pass through your body, and the Earth itself without a trace. Yet in the chaos of a dying star, they become cosmic energy bandits, carrying away up to 99% of a supernova's heat in a single, invisible surge. This isn't just a stellar curiosity, it's a fundamental flaw in our accounting of the universe's thermal budget. If we can't track where neutrinos take that energy, we're missing a colossal piece of the cosmic puzzle. Take a collapsing star's core. As gravity crushes it inward, protons and electrons merge into neutrons, releasing a flood of neutrinos in the process. These particles escape at nearly the speed of light, draining the star's core of energy that should, by all rights, contribute to the explosion's visible fireworks. When supernova 1987 lit up the sky, detectors on Earth caught a fleeting pulse of neutrinos arriving hours before the light, proof that these particles were the first messengers of the star's death. But here's the catch, the energy they carried didn't match the blast's expected fury. Somewhere between the core's collapse and the outer layers exploding, heat vanished without a trace. The mystery deepens when we zoom out to the universe's large-scale structure. Neutrinos born in the Big Bang still zip through space today, their combined mass subtly bending the paths of galaxies and galaxy clusters. Some models suggest these relic neutrinos could be warping the cosmic microwave background's temperature patterns, leaving faint imprints from their journey through 14 billion years of expanding space. Even stranger, certain theories propose that neutrinos might oscillate into sterile versions particles that interact only via gravity, creating hidden reservoirs of heat that evade detection entirely. What if neutrinos aren't just passive bystanders but active sculptors of the cosmos? In the early universe, their relentless motion may have prevented matter from clumping too quickly, delaying the birth of the first stars and altering the thermal history of everything that followed. Today, high-energy neutrinos from black holes and colliding galaxies punch through space, potentially depositing heat in unexpected pockets of the void. We're only beginning to map their routes with detectors buried in Antarctic ice and submerged in Mediterranean waters, chasing particles that could rewrite our understanding of cosmic thermodynamics. The real shocker, neutrinos might not even play by the same rules everywhere. Quantum mechanics allows for the possibility that their properties change in extreme environments, like near a black hole's event horizon or in the seething plasma of a quasar. If neutrinos behave differently under these conditions, they could be redistributing heat in ways our models never anticipated. Imagine a universe where the coldest regions aren't empty at all, but filled with neutrinos hoarding stolen warmth, or where dark matter particles only interact through neutrino intermediaries, creating invisible thermal currents that shape galaxies from the shadows. Every unanswered question about neutrinos is a crack in our understanding of cosmic temperature, from supernova that explode too quietly to the unexplained heating of intergalactic gas. These particles challenge the very definition of heat itself. As next-generation detectors come online, we might finally catch neutrinos in the act, revealing not just where they've hidden the universe's missing energy, but how they've been quietly puppeteering its evolution all along. The sun's surface simmers at a toasty 5,500 degrees Celsius, hot enough to vaporize rock, yet its outer atmosphere, the corona, burns millions of degrees hotter. This isn't just a stellar oddity, it's a full-blown cosmic contradiction. Picture holding your hand near a candle flame. The closer you get, the more heat you feel, right? But the sun flips this logic on its head. Its searing corona stretches far above the relatively cooler surface, like a campfire where the air 10 feet away is somehow hotter than the flames themselves. Scientists call this the coronal heating problem, and it's one of the most persistent puzzles in astrophysics. What could possibly fuel such extreme temperatures? One leading theory points to the sun's tangled magnetic fields. Imagine the surface boiling with plasma, a churning sea of charged particles. As these currents twist and snap like overstretched rubber bands, they release explosive bursts of energy, solar flares and smaller nanoflares that superheat the corona. It's as if the sun has an invisible network of energy highways, funneling heat outward against all expectations. Recent satellite observations have even captured ultrafine magnetic loops collapsing in the corona, sparking sudden temperature spikes like invisible match strikes. But there's a twist. Not all heating is created equal. During periods of low solar activity, when flares are rare, the corona somehow stays blisteringly hot. This suggests a second, quieter mechanism might be at work, perhaps waves of energy rippling outward from the sun's turbulent interior. Think of it like ocean waves carrying energy across vast distances, but instead of water, these are plasma waves transferring heat without the drama of explosions. The stakes go far beyond our solar backyard. If we can crack the sun's heating mystery, it could explain why other stars, especially those with wild magnetic activity, show even more extreme temperature mismatches. Some distant stars have coronas hundreds of times hotter than their surfaces, with flares so powerful they'd sterilize nearby planets. Understanding these dynamics could help us predict space, whether that threatens satellites, or even uncover why some stars are more prone to violent outbursts than others. Here's the kicker: we might be missing a fundamental piece of plasma physics. Laboratory experiments on Earth struggle to replicate the sun's conditions, leaving gaps in our models. Some theorists speculate that undiscovered particle interactions or microscopic reconnections in the sun's magnetic field could be leaking energy in ways we can't yet measure. Others wonder if the corona's heat is a quantum effect, with particles behaving differently under extreme magnetic pressures. Every solar mission, from probes diving through the corona to telescopes mapping its magnetic dance, brings us closer to answers. But the sun guards its secrets fiercely. Each discovery, like the recent detection of campfires, tiny, ubiquitous flares dotting the corona, raises new questions. One thing's certain: the sun isn't just a ball of gas. It's a dynamic magnetic furnace, challenging us to rethink how energy moves through the cosmos, one scorching mystery at a time. Some corners of the cosmos feel like nature forgot to pay the heating bill, vast stretches of space where temperatures plunge far below what our models predict. These cosmic cold spots aren't just empty voids, they're deep freezes that challenge everything we know about how energy moves through the universe. Take the Boötes Void, a spherical region nearly 330 million light-years wide containing almost no galaxies. You'd expect it to be cold, but not this cold. Its temperature dips lower than even the sparse distribution of matter can explain, as if some unseen force is actively siphoning away heat. What could possibly create such profound chill? One possibility lies in the ghosts of ancient superclusters. When massive galaxy clusters formed in the early universe, their gravity pulled in surrounding matter like cosmic whirlpools, leaving behind underdense regions that expanded faster than the rest of space. As these voids grew, the photons passing through them stretched to longer, colder wavelengths, a phenomenon called the integrated Sachs-Wolf effect. But some cold spots are too extreme for this alone to account for. That's where things get weird. Quantum entanglement, normally confined to subatomic particles, might operate on scales we never imagined. If particles separated by millions of light-years remain mysteriously linked, as some interpretations of quantum theory suggest, their interactions could redistribute thermal energy in ways that leave certain regions unnaturally frigid. Picture two dice always landing on matching numbers no matter how far apart they're rolled, except here, the rolls determine how heat flows across galactic distances. It sounds like science fiction, but measurements of the cosmic microwave background show temperature patterns that eerily align with predictions for large-scale quantum connections. Then there's the dark flow mystery. Clusters of galaxies appear to stream toward certain points beyond the observable horizon, as if pulled by structures so massive they warp the fabric of space itself. If these unseen attractors exist, their gravity might be stretching spacetime in ways that cool intervening voids, like wind chill on a cosmic scale. Alternatively, cold spots could be scars from primordial phase transitions, moments when the early universe's fundamental forces froze into their current states, creating defects in spacetime that still leak thermal energy into other dimensions. The coldest spot of all might be the most telling. In the constellation Eridanus lies a region of the cosmic microwave background that's 70 microkelvin cooler than its surroundings, a tiny difference with enormous implications. Some theorists argue this could be evidence of a collision with another universe during inflation, a bruise left by a parallel cosmos brushing against our own. Others propose it's the shadow of a cosmic texture, a knot in spacetime's fabric formed when the early universe's symmetry broke imperfectly. What makes these cold spots so revolutionary isn't just their temperature, it's their defiance. They resist explanation by dark matter, dark energy, or any known physics, pointing toward phenomena we haven't even named yet. Future telescopes like the European Space Agency's Euclid mission will map these regions in unprecedented detail, searching for hidden patterns in the chill. Until then, one thing's certain: the universe's coldest corners aren't just empty. They're blackboards scribbled with equations we haven't learned to read, and the answers might rewrite thermodynamics itself. The vacuum of space feels like the ultimate cold void, but quantum physics reveals a startling truth: nothing is ever truly empty. What seems like stillness is actually a seething quantum foam, where particles and antiparticles flicker in and out of existence so fast we can't detect them directly. These aren't just ghostly apparitions, they might be the universe's hidden heating system. Every cubic centimeter of so-called empty space contains enough of this vacuum energy to, in theory, boil the oceans, if only we could tap into it. How does this quantum chaos translate to heat? Imagine space as a stormy ocean. Even on a calm day, waves constantly form and vanish. In quantum terms, these waves are particle pairs, electrons and positrons, quarks and antiquarks, borrowing energy from the universe before annihilating and returning it. Normally, they cancel out perfectly, but near massive objects like stars or black holes, gravity distorts this balance, creating an asymmetry. Some particles get swallowed by the gravitational pull while others escape, leaving behind a faint but measurable energy. This is the Unravel effect. The warmer empty space gets, the more these quantum ripples behave like real particles, generating heat from pure nothingness. The implications are staggering. If vacuum energy permeates everything, it could explain why the universe isn't colder. Cosmic expansion should have diluted heat to near absolute zero by now, yet pockets of warmth persist. Some theorists argue that quantum fluctuations act like microscopic furnaces, constantly replenishing lost energy. Others take it further. What if dark energy, the mysterious force accelerating the universe's expansion, is actually vacuum energy in disguise? The math doesn't quite line up yet, but the idea tantalizingly links two of cosmology's biggest puzzles. Even more radical is the notion that vacuum heat isn't uniform. Certain quantum gravity models suggest spacetime itself has a granular structure at the smallest scales, like pixels on a screen. In regions where this structure is distorted, near black holes or in the early universe, vacuum energy might concentrate, creating thermal hotspots. Picture wringing out a sponge, twist spacetime enough, and hidden warmth could seep out. This might explain anomalous heat signatures around cosmic voids, or why some neutron stars appear slightly warmer than our models predict. Here's the twist: we might already be swimming in this quantum warmth without realizing it. The Casimir effect, where two metal plates placed micrometers apart in a vacuum inexplicably pull toward each other, is direct evidence of vacuum energy's push and pull. If these tiny forces can move objects, could they also be subtly heating interstellar gas or nudging atoms into higher energy states? The answer might lie in next-generation quantum sensors, designed to measure energy fluctuations so faint they've been invisible until now. The real mystery isn't whether vacuum energy exists, it's how much it shapes the cosmos. From the birth of galaxies to the fate of black holes, this quantum simmer could be the invisible hand guiding the universe's temperature. And if we ever learn to harness it, the coldest corners of space might not feel so cold after all. The universe doesn't just get hot, it rewrites the rules of heat entirely. Take quasars, the raging hearts of distant galaxies, where supermassive black holes shred entire stars into glowing plasma. The accretion disks around these monsters can hit temperatures of trillions of degrees, turning matter into a supercharged soup of particles moving near light speed. But what makes these cosmic furnaces burn so brightly? It's a combination of sheer gravitational might and friction on an unimaginable scale. As gas and dust spiral inward, they collide violently, converting kinetic energy into heat so intense it outshines entire galaxies. Then there's the fleeting inferno of neutron star collisions. When these ultra-dense stellar corpses slam together, they don't just merge, they detonate in a kilonova, a fireball so hot it briefly rivals the Big Bang. For a fraction of a second, temperatures soar past 10 trillion degrees, forging heavy elements like gold and platinum in the process. This isn't just a spectacle, it's a cosmic alchemy lab, where the universe's most extreme conditions transform simple matter into the building blocks of planets and life itself. But how do these events defy the limits of cooling? In most cases, heat radiates away quickly, yet quasars and merging neutron stars sustain their fury through sheer energy density. Picture a bonfire versus a blast furnace. The difference lies in how tightly energy is packed. In the accretion disk of a quasar, matter is compressed so densely that photons, the particles of light, can't escape easily. They bounce around like pinballs, heating the disk further in a feedback loop of thermal chaos. Meanwhile, neutron star collisions tap into the energy stored in their insane density. A single teaspoon of neutron star material weighs as much as a mountain, and when that mass converts to energy, the numbers defy intuition. These extremes don't just burn, they sculpt the cosmos. Quasar winds, powered by their unbearable heat, can blow gas out of galaxies entirely, shutting down star formation and leaving behind cosmic dead zones. The shockwaves from neutron star mergers seed galaxies with precious metals, enriching future generations of stars and planets. Even the radiation they emit shapes the surrounding space, ionizing atoms and stripping electrons in a cascade of particle violence. What's truly mind-bending is how these phenomena test the boundaries of known physics. At temperatures trillions of times hotter than the sun's core, matter behaves in ways we can't replicate in labs. Quasars might reveal how black holes influence galaxy evolution, while neutron star mergers could help us crack the equation of state for nuclear matter, the secret recipe governing how particles interact under impossible pressure. Some theories even suggest these events might briefly create quark-gluon plasma, a state of matter last seen microseconds after the Big Bang. The lesson here isn't just about raw power, it's about transformation. The universe's hottest places aren't just destructive, they're creative forces forging new elements, shaping galaxies, and pushing the limits of what's physically possible. And as telescopes like the James Webb Space Telescope peer deeper into these cosmic firestorms, we're not just watching heat, we're witnessing the universe's most violent, beautiful acts of reinvention. The ice giants lurking beyond our solar system don't just defy expectations, they shatter them. Picture Jupiter but frozen. Planets so massive they could swallow Earth whole, yet so cold that even their atmospheres freeze solid in layers. These cold Jupiters orbit so far from their stars that sunlight barely touches them, with surface temperatures plunging below -200 degrees Celsius. But here's the paradox: many of these worlds shouldn't exist at all. According to classic planetary formation theories, gas giants born in the frosty outskirts of star systems should have drifted inward over time, drawn by their star's gravity. Yet these icy behemoths cling to their distant orbits like cosmic sentinels, whispering secrets about the unseen forces sculpting planetary systems. What keeps these frozen titans so cold? For starters, their atmospheres are loaded with methane, ammonia, and water ice molecules that act like thermal blankets, trapping what little heat they have and preventing it from escaping. But the real kicker is their internal dynamics. Unlike gas giants in our solar system, which generate heat through slow gravitational compression, many cold Jupiters seem geologically stagnant. Without churning metallic hydrogen cores or raging storms to redistribute energy, their heat gets locked away, leaving their upper atmospheres eerily still. Some even exhibit inverted weather, where higher altitudes are colder than the depths below, a phenomenon that turns atmospheric science on its head. Then there's the wild card: tidal heating. Moons orbiting these ice giants could be flexing their host planets' interiors through gravitational tug-of-wars, generating subsurface warmth that occasionally bubbles up as cryovolcanoes. Imagine a world where volcanoes spew liquid nitrogen instead of lava, painting landscapes in frosty plumes. This delicate balance between external chill and internal flickers of heat might explain why some cold Jupiters sport faint auroras. Ghostly light shows powered not by solar wind, but by interactions with their own icy moons. The most tantalizing clue lies in their birthplaces. These planets likely formed in protoplanetary disks rich in icy debris, where temperatures were low enough for volatile compounds to freeze onto dust grains. As they grew, they hoarded these ices, creating layered atmospheres with exotic climates. Some models suggest they might even harbor hidden oceans beneath their frozen shells, kept liquid by extreme pressures or chemical antifreezes like ammonia. If true, it would mean the galaxy's coldest giants could, paradoxically, host the very ingredients for life, just not as we know it. What makes these worlds revolutionary isn't just their chill, it's what they reveal about cosmic diversity. For every scorching, hot Jupiter we've found, there's likely a frozen counterpart, proof that planetary systems can evolve along wildly different thermal pathways. Future telescopes like the Habitable Worlds Observatory will probe their atmospheres for biosignatures, testing whether life could emerge in the unlikeliest of freezers. Until then, one thing's clear: the universe's ice giants aren't just outliers. They're a window into the infinite creativity of planetary physics, where cold isn't the end of the story, but the beginning of something far stranger. Long before galaxies filled the cosmos, the universe lurked in a fog, a sea of neutral hydrogen atoms so thick they absorbed all light, trapping the young cosmos in darkness. Then, suddenly, something switched on the heat. Between about 50 million and 1 billion years after the Big Bang, this primordial fog burned away as hydrogen atoms were violently stripped of their electrons, a process called reionization. But what cosmic force could possibly generate enough heat to sterilize an entire universe? The answer lies in the first extreme objects to emerge from the darkness, and their identities remain one of astrophysics' fiercest debates. The prime suspects, population 3 stars, hypothetical giants hundreds of times more massive than our Sun. Born from pure hydrogen and helium without contaminating metals, these behemoths would have lived fast and died violently, their ultraviolet radiation shredding surrounding hydrogen like tissue paper. Picture a match struck in a pitch-black room, except this match is a star hotter than anything in today's universe, and the room is 100,000 light-years across. The problem: we've never directly observed these stars. They vanished long ago, leaving behind only chemical fingerprints in the oldest galaxies and the ghostly afterglow of their ionizing fury. Yet stars might not be the only arsonists. Early supermassive black holes, feeding greedily on surrounding gas, could have unleashed torrents of X-rays capable of ionizing hydrogen far beyond their host galaxies. Recent observations of distant quasars bright enough to pierce the reionization era show they were surprisingly common back then. If even a fraction of these monsters existed in the universe's first chapters, their combined radiation might have reheated the cosmos like microwaves thawing frozen soup. Then there's the dark horse candidate, dark matter annihilation. If certain theoretical particles collided and destroyed each other in the early universe, they could have flooded space with high-energy photons, providing an invisible heat source that jump-started reionization from within the cosmic fog itself. It's a radical idea that the universe's greatest transformation might have been fueled by particles we still can't detect. The stakes couldn't be higher. Reionization didn't just clear the fog, it set the stage for every galaxy, star, and planet that followed. Too much heat too early, and delicate gas clouds would have blown apart before forming modern galaxies. Too little, and the universe might have remained shrouded in darkness indefinitely. The Goldilocks timing of this event suggests an exquisite balance, one that future telescopes like the James Webb Space Telescope are now probing by hunting for the faintest, most ancient light. What makes this mystery so thrilling is its lingering echoes. The uneven way reionization unfolded, patchy, bubbly, with some regions ionizing faster than others, left scars in the distribution of galaxies we see today. By mapping these cosmic fossils, we're not just solving a puzzle about heat, we're reading the origin story of structure itself. And hidden in that story might be the answer to why our universe looks the way it does, a masterpiece painted in strokes of searing light and primordial shadow. Time's arrow points relentlessly toward chaos, a cosmic rule so fundamental that it governs everything from melting ice cubes to dying stars. The second law of thermodynamics isn't just a suggestion. It's the universe's way of ensuring heat always spreads out, energy always degrades, and disorder always increases. This is entropy, the hidden tax on every process in existence. But here's the twist. While entropy dictates that heat must disperse, the universe has spent billions of years building pockets of exquisite order, galaxies, planets, life itself. How does this paradox hold, and what does it mean for the ultimate fate of everything? Picture a campfire on a cold night. The flames leap high, radiating warmth in all directions, but eventually the logs burn to ash and the heat dissipates into the darkness. Now scale that up to cosmic proportions. Stars are the universe's campfires, fusing hydrogen into helium and radiating light for eons. But like all fires, they'll eventually exhaust their fuel. White dwarfs will cool into black dwarfs, black holes will evaporate via Hawking radiation, and even the cosmic microwave background, the last whisper of the Big Bang, will fade into silence. This is the heat-death scenario, a future where the universe reaches maximum entropy, a state of perfect equilibrium where no energy can be extracted, no work can be done, and no change can occur. It's not an explosion or a collapse, just an endless, featureless twilight. But what if entropy isn't the end of the story? Some cosmologists propose a far wilder idea, that the universe might be cyclical, with each death giving birth to a new cosmos. Imagine entropy not as a one-way street, but as a roller coaster. In these models, when the universe reaches maximum expansion, dark energy could decay, reversing the arrow of time and triggering a big crunch. All matter and energy would collapse back into a singularity, resetting entropy to zero and sparking a new Big Bang. It's a cosmic phoenix, rising from its own ashes, except instead of flames, it's reborn from cold, empty stillness. The evidence for this remains speculative, but tantalizing clues linger. Certain interpretations of quantum gravity suggest that black holes might not be ultimate endpoints, but portals to new universes with their own physical laws. If true, entropy could leak between these realities, preventing true heat death. Others argue that the universe's initial low entropy state, a mystery in itself, hints at a prior cycle, like a shuffled deck of cards returning to order. Even string theory offers possibilities, with colliding brains, higher dimensional objects, potentially spawning new universes in collisions that reset the entropic clock. What makes these ideas so compelling isn't just their audacity, it's their defiance of inevitability. Heat death assumes our universe is a closed system, but what if it's not? Could quantum fluctuations in the far future spawn new Boltzmann brains, conscious entities emerging from random particle arrangements to observe a reborn cosmos? Or might dark energy's grip weaken over time, allowing gravity to pull everything back together? The answers lie in the subtle patterns of the cosmic microwave background, the behavior of distant supernova, and the quantum foam at spacetime's smallest scales. One thing's certain, entropy isn't just a force of decay. It's the engine of complexity, the reason time moves forward, and the hidden hand shaping everything from snowflakes to superclusters. Without it, stars wouldn't shine, life wouldn't evolve, and the universe would be a stagnant sea of uniformity. So while heat death looms in theory, the story of entropy is far from written. It might just be the prologue to a cycle we're only beginning to imagine, where every ending carries the seed of a new beginning. Bose-Einstein condensates sound like something ripped from a sci-fi novel, a state of matter where atoms lose their individuality and merge into a single quantum wave, behaving less like particles and more like ghostly ripples in reality. On Earth, creating these condensates requires temperatures just a whisper above absolute zero, achieved only in labs with lasers and magnetic traps. But what if the universe has been brewing its own condensates all along, hiding them in the coldest corners of space? The answer could rewrite our understanding of quantum physics on a cosmic scale. Picture a cloud of atoms so cold they practically stop moving. As their thermal energy vanishes, their quantum wavelengths stretch until they overlap, like overlapping sound waves tuning into perfect harmony. This is the essence of a Bose-Einstein condensate, a superfluid where friction disappears, light slows to a crawl, and matter behaves as a single entity. While we've mastered creating these conditions in labs, nature might have its own recipes. The Boötes Void, a cosmic desert nearly devoid of galaxies, or the shadowy outskirts of nebulae where starlight barely reaches, could harbor pockets cold enough for condensates to form spontaneously. Even the interstellar medium, with its sparse atoms drifting through near vacuum, might flirt with these quantum states under the right conditions. The implications of finding condensates in space are staggering. Imagine a neutron star's magnetic field threading through a condensate of charged particles, creating superconductivity on a stellar scale. Or dark matter, if it interacts weakly enough, pooling into Bose-Einstein puddles in the voids between galaxies, invisible yet sculpting the cosmos through quantum coherence. Some theorists even speculate that condensates could form in the relic radiation left by black hole evaporation, where temperatures approach the coldest possible limits. But how would we detect such phenomena? Traditional telescopes can't see condensates directly, but their influence might leave telltale signatures. A condensate bending light in unexpected ways, or emitting distinct low-energy photons as it transitions between quantum states, could betray its presence. Recent proposals suggest looking for anomalies in the polarization of cosmic microwave background radiation, subtle twists that might reveal quantum fluids stretching across ancient space. The real magic lies in what condensates could teach us. If they exist naturally, they'd prove that quantum weirdness isn't confined to microscopic scales. It can emerge across light years, governing the behavior of matter in ways Einstein and Bose never imagined. From the birth of galaxies to the fate of black holes, these ghostly quantum states might be silent players in the universe's grand drama, waiting for us to tune into their frequency. And if we listen closely, the cosmos might just whisper its coldest, most elusive secrets. The silence of the cosmos might be hiding something far stranger than we imagined. If the universe is truly teeming with intelligent life, where are the heat signatures of their megastructures, the infrared glow of their sprawling cities? This is the thermal twist on the Fermi paradox, not just where is everybody, but why isn't there waste heat lighting up the sky? The answer could lie in the terrifying possibility that cosmic temperatures aren't just a backdrop for life, they're a filter that eliminates it. Consider the Kardashev scale, which ranks civilizations by how much energy they harness. A Type 2 civilization might build Dyson spheres around stars to capture every photon of light. Our telescopes should spot these cosmic furnaces, yet the infrared sky remains suspiciously dark. One explanation: advanced societies might have cracked quantum energy harvesting, tapping vacuum fluctuations or dark matter with near-perfect efficiency. Imagine a technology so refined it leaves no thermal footprint, like a car that runs without exhaust. If true, the universe could be buzzing with life we're literally too primitive to detect. But there's a darker interpretation. The Great Filter theory suggests something prevents life from progressing beyond a certain point, and temperature extremes could be that barrier. Early civilizations might emerge during their planet's thermal golden age, only to be wiped out when their star flares, their atmosphere freezes, or their oceans boil. Even if they survive, the leap to interstellar travel could require energy output so vast they'd cook their own biosphere. We might be alone not because life is rare, but because the universe is ruthlessly good at sterilizing it. Then there's the haunting possibility of self-destruction. Nuclear war or climate collapse could be universal bottlenecks. Any civilization that burns fossil fuels or splits the atom might inevitably trigger a thermal tipping point. The Milky Way's silent expanse could be a graveyard of civilizations that failed to balance energy use with planetary thermodynamics. Or worse, what if predatory civilizations actively suppress others by overheating their worlds? A single rogue AI could turn entire star systems into thermal weapons, frying emerging life before it becomes a threat. Yet hope isn't lost. Some exoplanets orbit in terminator zones, where one side is eternally scorched and the other frozen. Life there would need to master temperature gradients to survive, a skill that might scale to cosmic engineering. Others propose that advanced beings transcend biology, uploading consciousness into quantum substrates that thrive near absolute zero. The universe's quiet might not be absence but evolution. The chilling truth, we're playing thermal roulette without knowing the rules. Every watt of energy we release into space is a beacon announcing our presence. Whether that's an invitation or a death sentence depends on how hot or how cold the universe really wants us to be. Magnetic fields are the universe's invisible puppeteers, pulling strings we've only just begun to see. They twist through galaxies like cosmic spiderwebs, channeling heat with such precision that a wisp of gas can be superheated to millions of degrees without a single star nearby. Take the Perseus galaxy cluster, where magnetic fields have been caught red-handed, turning turbulence into thermal energy, like an invisible hand stirring a pot until it boils. This isn't just physics, it's a revolution in how we understand the cosmos's thermal budget. How does a magnetic field become a cosmic heater? Picture the turbulent plasma between galaxies, a soup of charged particles seething with motion. As these particles spiral along magnetic field lines, they collide and release energy in a process called magnetic reconnection. Think of it as a short circuit on an interstellar scale. NASA Chandra X-ray Observatory has spotted these events, unleashing flares hotter than the sun's core, all from what looks like empty space. But the real magic happens when these fields act like traps, corralling particles into high-pressure zones where friction cooks them to extreme temperatures. It's as if the universe has built invisible furnaces stoked by magnetism itself. The most baffling examples lie in the hearts of galaxy clusters. Here, magnetic fields don't just heat gas, they prevent it from cooling. Observations show that some clusters should have cooled enough to form torrents of new stars, yet their cores remain scorching. The culprit, magnetic turbulence, stirring the pot so vigorously that heat can't escape. This feedback loop might explain why the universe hasn't drowned in starlight, because magnetism keeps turning up the thermostat. Then there's the wild card, magnetic dynamos. When galaxies collide, their tangled fields can amplify to strength rivaling neutron stars, creating shock waves that heat surrounding gas like a cosmic pressure cooker. The Atacama Large Millimeter Array recently caught two galaxies in the act, their magnetic fields sparking temperatures so extreme they outshone the galaxy's own stars. If this is common, it could mean that galactic mergers aren't just about gravity, they're magnetic fireworks repainting the thermal map of the universe. What's truly mind-bending is how these fields scale. From the delicate filaments threading sunspots to the vast webs connecting galaxy clusters, magnetism operates at every level, transferring heat in ways that defy intuition. Some theorists even suggest that primordial magnetic fields, forged in the Big Bang's first seconds, might still be lurking in deep space, subtly guiding how the universe distributes its energy. The lesson here is humbling. We've spent centuries studying stars and black holes as the universe's primary heat sources, while magnetism worked its magic in the shadows. Now, as telescopes like the Square Kilometre Array come online, we're peering into this hidden realm, where the coldest voids and hottest plasma are connected by threads of invisible force. And what we're finding suggests that if you want to understand cosmic temperature, you don't just look at the light, you follow the magnetism. Dark matter might be the universe's ultimate ghost, invisible, intangible, yet shaping galaxies with its gravitational pull. But what if its influence goes deeper than gravity? What if this mysterious substance is quietly stealing heat from the cosmos, leaving behind a thermal fingerprint we've only just begun to trace? The idea that dark matter could interact with thermal energy isn't just speculative. It's a radical reimagining of how the universe balances its books. Think of space as a vast network of invisible threads where dark matter forms a scaffold for galaxies. Normally, these threads don't just ignore light, they ignore heat too. But some theories propose that certain types of dark matter particles could absorb or scatter thermal energy, like a sponge soaking up water. Imagine a room where the temperature drops inexplicably in certain corners, not because of a draft, but because something unseen is siphoning away warmth. On a cosmic scale, this could explain why some galaxy clusters appear slightly cooler than our models predict, as if patches of dark matter are leaching heat from the surrounding gas. The hunt for this thermal shadow is already underway. Scientists are scrutinizing the cosmic microwave background for anomalies, subtle dips in temperature that align with predicted dark matter concentrations. Other teams are studying the way heat distributes in galaxy clusters, searching for regions where energy seems to vanish without a trace. The most tantalizing clues come from simulations suggesting that dark matter might not be entirely cold. Some models propose a fraction of it could be warm, with particles just light enough to interact weakly with photons, subtly altering the thermal landscape of the universe. Here's where it gets even stranger. If dark matter does interact with heat, it might not just absorb energy, it could re-emit it in unexpected ways. Picture a hidden cosmic radiator where dark matter particles collide and release low-energy photons, warming pockets of space we assumed were cold. This could explain why some interstellar clouds glow faintly in wavelengths that don't match any known light source. The implications are staggering. Dark matter might not just be a passive spectator in the universe's thermal drama. It could be an active player, quietly redistributing heat in ways we're only beginning to grasp. The real breakthrough would come from detecting this interaction directly. Next-generation telescopes like the Vera-C, Rubin Observatory are poised to map the sky with unprecedented precision, potentially spotting the thermal fingerprints of dark matter in the faintest glows of distant gas clouds. Meanwhile, underground detectors are searching for the faintest heat signatures left by dark matter particles brushing against ordinary atoms. If either effort succeeds, it wouldn't just confirm dark matter's existence, it would reveal how it shapes the universe's temperature, one invisible touch at a time. The irony is delicious. Dark matter, long thought to be utterly indifferent to light and heat, might hold the key to understanding why the cosmos cools the way it does. And if we're right, the universe's coldest shadows could finally illuminate its darkest secret. Somewhere beyond the stars, an invisible leviathan is tugging at our galaxy, along with thousands of others, in a slow-motion cosmic tug of war. Astronomers call it the Great Attractor, a gravitational anomaly so powerful it bends the motion of entire galaxy clusters toward it. But gravity isn't the only force at work here. Hidden in this mysterious region, roughly 250 million light-years away, lies a thermal puzzle that could rewrite our understanding of how the universe distributes heat. Normally, massive galaxy clusters glow fiercely in X-rays, their gas heated to millions of degrees by gravitational compression and collisions. Yet the Great Attractor's core is oddly dim, as if something is masking its thermal signature. One tantalizing possibility, dark matter, lots of it colliding and annihilating in ways we've never observed. Picture two invisible particles slamming together and transforming into bursts of gamma rays which then heat surrounding gas. This could explain why telescopes spot faint, diffuse warmth spread across the region rather than concentrated hotspots. It's like finding a room warmed by unseen radiators, their heat radiating from nowhere and everywhere at once. But dark matter isn't the only suspect. The Great Attractor sits behind the Milky Way's dusty disk, in a zone astronomers call the zone of avoidance because our galaxy's bulk obscures the view. What if hidden galaxies or black holes there are generating heat through violent mergers, their energy smeared into a subtle glow by intervening dust? Recent infrared surveys have pierced this cosmic veil, revealing hints of massive structures previously invisible to us. If these objects are stirring the gravitational pot, their friction could be cooking the surrounding medium to temperatures we're only now detecting. The strangest twist, the Great Attractor might not be the final destination. Some models suggest it's just a waypoint on a far larger journey with an even more massive structure, the Shapley supercluster lurking beyond it. If true, the heat we're detecting could be a side effect of this grand cosmic traffic jam, where galaxies pile up like cars on a freeway, their gravitational energy dissipating as warmth. Solving this mystery isn't just about mapping the unseen. It's about understanding how the universe's largest structures transfer energy across billions of light years. Future telescopes, like the European Space Agency's Athena X-ray Observatory, aim to dissect this region's thermal fingerprints in exquisite detail. What they find could reveal whether dark matter truly interacts with itself, or if entirely new physics is at play in the cosmos's hidden corners. For now, the Great Attractor remains a paradox, a gravitational giant that refuses to show its full thermal hand. But every flicker of warmth we detect is a clue, a whisper from the darkness hinting at forces we've yet to name. And in that whisper, there might just be the key to understanding how the universe's largest structures keep the cosmic engine running. Gamma-ray bursts are the universe's ultimate flashbangs, blinding eruptions of energy so intense they outshine entire galaxies for a few fleeting seconds. In that brief window, these cosmic detonations unleash more power than our sun, will radiate over 10 billion years, packing temperatures that reach trillions of degrees. What could possibly fuel such apocalyptic heat? The answer lies in the death throes of massive stars or the cataclysmic mergers of neutron stars, events so violent they warp the very laws of physics as we know them. Take a collapsing hypergiant star, its core exhausted of nuclear fuel. As gravity overwhelms it, the star doesn't just implode, it transforms into a cosmic particle accelerator. Jets of plasma, narrower than a pencil but stretching light years long, punch through the dying star at nearly the speed of light. These jets are so focused and energetic that their collisions generate gamma rays, the most powerful form of light. The temperatures here dwarf anything in our solar system, creating conditions where matter and antimatter spontaneously materialize from pure energy. It's like a nuclear bomb detonating inside a supernova with physics stretched to its breaking point. But the real shocker is what happens next. As these jets plow through interstellar space, they don't just fade, they ignite the surrounding gas like a match tossed into gasoline. The afterglow, visible for days or weeks in X-rays and radio waves, reveals shock waves rippling through the cosmos, heating everything in their path to millions of degrees. Astronomers have even caught gamma-ray bursts reheating their own remnants, as if the explosion refuses to die quietly. Some of these events leave behind black holes, their birth cries echoing across the universe in waves of extreme heat. What makes these bursts so revolutionary isn't just their power, it's their precision. The energy isn't sprayed randomly, it's focused into beams narrower than a laser pointer. If one of these jets happened to point at Earth from thousands of light years away, the radiation could strip our atmosphere of ozone, triggering mass extinctions. Thankfully, most bursts are too distant to threaten us, but their sheer frequency, about one per day somewhere in the observable universe, suggests they've played a role in shaping cosmic history. Some theories propose that early gamma-ray bursts might have sterilized entire galaxies, preventing life from emerging until the universe cooled enough to make these events rarer. The most tantalizing possibility: these bursts could be natural particle colliders, reaching energies far beyond anything we can replicate in labs. In their heart of hearts, exotic states of matter might form quark-gluon plasma, or even hints of extra dimensions predicted by string theory. By studying the light curves and spectra of these explosions, scientists are reverse engineering the physics of the universe's most extreme environments, testing theories about gravity, quantum mechanics, and the birth of elements like gold and platinum. Here's the kicker: we're only seeing part of the picture. Current telescopes catch the afterglows, but the initial burst, lasting just milliseconds, often slips through our nets. New missions like NASA's Swift satellite and the upcoming European Space Agency's Theseus aim to catch these events in their infancy, peeling back the layers of the universe's most violent heat engines. Every flash holds clues not just about stellar death, but about the fundamental forces that govern heat, light, and time itself. And hidden in those clues might be answers to questions we haven't even thought to ask yet. Before time itself had meaning, before the first tick of the cosmic clock, the universe existed in a state so extreme it defies imagination: the Planck era. Here, in the first 10 to the minus 43 seconds after creation, temperatures reached a staggering 10 to the 32 degrees Kelvin, a heat so intense that the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were indistinguishable, fused into a single, unified superforce. This wasn't just a hotter version of the universe we know. It was a realm where space and time lost their definitions, where energy and matter were one and the same, flickering in and out of existence like quantum mirages. To grasp the sheer extremity of this epoch, picture the entire observable universe compressed into a space smaller than a single atom. At these scales, the fabric of reality itself became foamy and uncertain, with microscopic black holes forming and evaporating in a frenzied dance governed by quantum fluctuations. The very concept of temperature as we understand it breaks down here, because the particles we associate with heat, photons, quarks, electrons, couldn't yet exist. Instead, the universe was a seething cauldron of pure energy, where the distinction between past and future blurred into irrelevance. The real mystery isn't just the heat, it's how the universe escaped it. As the cosmos expanded, it cooled, and around 10 to the minus 36 seconds, something extraordinary happened. The strong nuclear force peeled away from the others in a cataclysmic event called the Grand Unification Phase Transition. This was less like water turning to ice and more like reality itself rewiring its fundamental code. The energy released in this separation may have turbocharged cosmic inflation, stretching space exponentially in a fraction of a second and locking in the temperature fluctuations we now see in the cosmic microwave background. But the Planck era holds even deeper puzzles. Without a working theory of quantum gravity, we can't fully describe this epoch. String theory and loop quantum gravity offer competing visions. Perhaps the universe was a vibrating string or a spin network, but both suggest that space-time itself was born from this furnace, crystallizing as temperatures dropped. Some models even propose that the Planck era wasn't the absolute beginning, but a rebound from a previous universe's collapse, a cosmic phoenix rising from its own ashes. The echoes of this primordial inferno might still be detectable. Primordial gravitational waves, ripples in space-time from the universe's birth throes, could carry imprints of these unimaginable temperatures. Experiments like the Laser Interferometer Space Antenna aim to catch these whispers, while tabletop quantum gravity probes hunt for hints of spacetime's granular structure. If we succeed, we might finally glimpse the moment when heat wasn't just a property of the universe, it was the universe. What makes this era so mesmerizing isn't just its extremity, but its necessity. Every quark, every galaxy, every law of physics we take for granted was forged in this crucible. The Planck era didn't just set the universe's temperature, it wrote the rules for everything that followed. And somewhere in those first unknowable instants, the seeds were planted for a cosmos that could one day ask questions about its own origins. Our universe feels like the Goldilocks zone of temperatures, not too hot, not too cold, just right for stars to shine and life to emerge. But what if this balance isn't unique? What if it's just one setting in an infinite cosmic control panel, where every dial twists to a different thermal extreme? The multiverse theory paints a picture far stranger than alternate realities. It suggests a sprawling landscape of universes, each with its own laws of physics and, crucially, its own rules for heat. Imagine a universe where the strength of electromagnetism is slightly stronger. Atoms would bind more tightly, stars would burn hotter and faster, and the cosmos might blaze through its energy in a cosmic flash. Now picture the opposite, a sluggish universe where forces are weaker, matter struggles to clump together, and temperatures hover near absolute zero, a frozen wasteland where chemistry barely functions. These aren't just thought experiments, they're real possibilities in the string theory landscape, where up to 10 to the 500 distinct universes could exist, each with its own thermal destiny. The wildest part, some of these universes might not even recognize our concept of temperature. In a reality with extra spatial dimensions, heat could dissipate in ways we can't fathom, like water draining through unseen cracks. Others might oscillate between extremes, with temperatures surging and crashing in cycles so vast they make ice ages look like flickers. There could even be universes where heat flows backward, reversing entropy and turning the arrow of time into a loop. The variations aren't just about degrees on a thermometer, they're about rewriting the fundamental rules of energy itself. How would we ever detect these thermal echoes beyond our cosmic horizon? One clue lies in the cosmic microwave background. Strange anomalies like the cold spot we discussed earlier could be bruises from collisions with other universes, their thermodynamics imprinting onto ours like shadows. Alternatively, if our universe is a bubble in a larger multiverse, the energy of its birth might have left faint thermal fingerprints in gravitational waves, subtle ripples we could one day measure with observatories like the Laser Interferometer Space Antenna. The most humbling thought, our universe's temperature might not be special, just statistically likely. In an infinite multiverse, most realities could be too hot or too cold for complexity to arise. We find ourselves in a universe that permits galaxies, planets, and life, not because it's the only option, but because it's one of the few where the question can even be asked. The multiverse doesn't just expand the canvas of reality, it turns thermodynamics into a choose-your-own-adventure story, where heat isn't a fixed rule, but a fleeting local custom in an endless cosmic bazaar. If black holes are the universe's drains, white holes could be its fire hoses, hypothetical cosmic geysers, violently ejecting matter and energy instead of trapping them. These bizarre objects, predicted by some solutions to Einstein's equations but never observed, flip the script on everything we know about cosmic thermodynamics. Picture a black hole in reverse, where gravity's grip is replaced by an unstoppable repulsion, a singularity that can't be entered, only exited. The heat output would be unimaginable, not the slow trickle of Hawking radiation, but a cataclysmic eruption of particles accelerated to near light speed, colliding and igniting space around them in a firestorm of gamma rays and superheated plasma. The implications for the universe's energy balance are staggering. Black holes notoriously hoard mass and energy, locking them away behind event horizons. White holes, by contrast, could act as cosmic pressure valves, recycling trapped energy back into the cosmos. Some theories even suggest that every black hole might be connected to a white hole via an Einstein-Rosen bridge, a wormhole where what's swallowed here emerges there, like a one-way tunnel through space-time. If true, the heat pouring out of white holes could explain mysterious high-energy events, like unexplained gamma-ray bursts with no visible source. Imagine a universe where every act of destruction is secretly paired with an act of creation, hidden somewhere beyond our observational horizon. But why haven't we found one? The math allows for white holes, but physics prefers order. A white hole's existence would require pristine conditions, a singularity untouched by external matter, free from the chaos of the cosmos. Even a single atom drifting into its event horizon could collapse it into a black hole, like a soap bubble popping at the slightest touch. That makes white holes fantastically unstable, possibly lasting mere seconds before vanishing. Yet their fleeting existence could still leave scars. Some astronomers speculate that fast radio bursts, those enigmatic millisecond flashes of radio waves, might be white holes' dying screams, their final bursts of energy redshifted across billions of years. The most radical idea, white holes might not just be relics of the past. Quantum gravity models suggest that when black holes finally evaporate via Hawking radiation, they could rebound as white holes in their final moments, transforming from ultimate absorbers into explosive emitters. If so, the universe could be dotted with microscopic white holes, remnants of primordial black holes from the Big Bang, each erupting like a champagne cork at the end of time. Their combined heat might subtly influence the cosmos's temperature, like invisible radiators humming in the void. Whether white holes are real or not, their theoretical existence forces us to confront a profound question. Does the universe keep perfect thermal accounting? If black holes sequester heat, could white holes balance the books? Or is the cosmos content to let energy disappear into singularities, leaving us to puzzle over the missing receipts? Until we spot one, or rule them out entirely, white holes remain the ultimate cosmic what if, a reminder that even in thermodynamics, every rule might have its exception. Consider the cosmic miracle of water, a molecule that shouldn't exist in liquid form across such a vast temperature range, yet does, purely because the forces binding its atoms align with near impossible precision. This isn't just chemistry, it's a signature of something far grander. Our universe operates within a razor-thin thermal window where stars burn steadily, planets retain atmospheres, and complex molecules can dance the delicate tango of life. Shift the strength of gravity by a hair, and stars would blaze too fiercely or fizzle out too soon. adjust the electromagnetic force slightly, and atoms would either refuse to bond or cling together irrevocably. Even the expansion rate of space itself is fine-tuned too fast, and matter never clumps into galaxies, too slow, and everything collapses into a fiery crunch before life gets a chance. The numbers behind this balance are staggering. The cosmological constant, which dictates how fast the universe expands, is calibrated to 1 part in 10 to the 120. That's like throwing a dart across the observable universe and hitting a bullseye the width of an atom. Meanwhile, the energy difference between protons and neutrons in atomic nuclei is just 2 parts in 1,000, a margin so slim that altering it would leave stars unable to forge carbon, the backbone of life. Even the universe's average temperature, hovering near 3 degrees above absolute zero, is a relic of this precision. Too much residual heat from the Big Bang, and galaxies would drown in radiation. Too little, and the cosmic web of structure might never have formed. But how did we land in this thermal sweet spot? One camp argues for the multiverse, a sea of universes with randomized constants, where we simply inhabit the one where the numbers permit our existence. It's the ultimate selection bias. We're here to ponder the odds because the odds allowed us to be here. Others propose a deeper principle, a yet unknown law of nature that locks these values into place, like cosmic gears meshing perfectly by design. Some even entertain the radical idea that consciousness itself plays a role, that universes fine-tune their parameters to foster observers in a self-reinforcing loop. The evidence isn't just philosophical. Look at Earth's position, not too close to the Sun's fury, not too far in the frozen dark, but in an orbital slot where water stays liquid and DNA remains stable. Extend that logic galaxy-wide. Spiral arms like ours offer shelter from the lethal radiation of the galactic core, while still providing enough heavy elements forged in stellar furnaces to build planets. Zoom out further, and you'll find our universe's large-scale structure filaments and voids creates pockets where temperatures fluctuate just enough to drive complexity, but not so wildly as to sterilize entire regions. Yet the most humbling thought isn't that we're lucky, it's that we might be inevitable. If the universe naturally trends toward conditions that allow self-replicating patterns to emerge, then life isn't a fluke. It's a thermodynamic endpoint, a way for the cosmos to comprehend itself. Every star, every planet, every molecule vibrating in the Goldilocks zone isn't just a beneficiary of cosmic fine-tuning, it's a participant in the universe's slow, beautiful awakening to its own existence. And that raises a question warmer than any star. If the universe is built to ask questions, what other answers might be waiting in the thermal whispers of the void? The next generation of cosmic explorers won't be astronauts. They'll be telescopes so advanced they can read the universe's thermal fingerprints like a forensic detective at a crime scene. Imagine an instrument so sensitive it could detect the heat of a single candle flickering on a moon of Jupiter, then zoom out to map the temperature fluctuations of entire galaxy clusters. This isn't science fiction. Projects like the European Space Agency's Ariel mission and NASA SPHEREX are already gearing up to scan the skies in infrared and submillimeter wavelengths, creating the most detailed thermal atlas of the cosmos ever attempted. But they're not just looking for heat, they're hunting for the invisible architecture of reality itself. Take the upcoming James Webb Space Telescope's successor, the Habitable Worlds Observatory. While Webb revolutionized our view of the early universe, this new instrument will specialize in detecting the faint thermal signatures of exoplanet atmospheres, chemical tracers like methane and ozone that could hint at alien biospheres. But it'll also do something far more profound. Measure how heat circulates on planets orbiting red dwarfs versus sun-like stars, testing whether life's thermal sweet spot is rare or universal. The same data might reveal if tidally locked worlds where one side forever bakes and the other freezes could harbor life in their twilight zones where temperatures balance on a knife's edge. Then there's the dark horse of cosmic thermography, quantum sensors. On Earth, devices like superconducting nanowire single-photon detectors are pushing the boundaries of heat measurement, capable of spotting individual photons with pinpoint energy precision. Scale this up to space, and we could have arrays that track the subtlest temperature variations in the cosmic microwave background, anomalies so faint they might trace the gravitational wakes of hidden dimensions or the evaporation trails of primordial black holes. Picture a thermometer so precise it could detect the universe's quantum foam frothing at spacetime's smallest scales, but the real game changer, multi-messenger astronomy. Future observatories won't just watch heat, they'll pair it with gravitational waves, neutrino bursts, and magnetic field maps to reconstruct cosmic events in 4D. When two neutron stars collide, for instance, combining thermal data with gravitational wave signals could reveal how much energy is converted to neutrinos versus gamma rays versus plain old heat, a breakdown that might expose flaws in our nuclear physics models. The same approach could crack the mystery of fast radio bursts. Are they the death cries of magnetars, the belches of black holes, or something far stranger? Thermal fingerprints don't lie. The boldest promise lies in uncovering entirely new energy forms. Some theories predict that dark matter particles, when annihilating, should release faint thermal whispers at specific frequencies. Others suggest that vacuum energy fluctuations, those quantum ripples in empty space, might leave nanoscale heat signatures when probed just right. If next-gen sensors spot these patterns, we could be staring at the universe's hidden power grid, dark energy reactors humming between galaxies or quantum entanglement transferring heat across light years instantaneously. What makes this thermal revolution so thrilling isn't just the technology, it's the questions we haven't thought to ask yet. Every time humanity has built a better thermometer, from Galileo's rudimentary thermoscope to Planck's all-sky microwave maps, we've stumbled upon phenomena that rewrite textbooks. As these new tools come online, they won't just map the cosmos's temperature, they'll force us to redefine what heat even means in a universe far wilder than we've dared to imagine. From the Big Bang's searing birth to the enigmatic cold spots of today, the universe's temperature isn't just a measurement, it's a language that tells the story of colliding galaxies, dying stars, and quantum whispers in the void. Every fluctuation, every extreme, from the trillion-degree infernos of neutron star mergers to the near-absolute zero stillness of cosmic voids, is a clue waiting to be decoded. And what we've uncovered so far is just the preamble. Consider this: the same cosmic microwave background that revealed the universe's infancy now hints at phenomena we can't yet explain. The cold spot, the axis of evil, the mismatched heat of galaxy clusters, these aren't just anomalies. They're breadcrumbs leading us toward a deeper truth, one where dark matter might exchange heat like a hidden currency, where vacuum energy simmers beneath spacetime's surface, and where the laws of thermodynamics themselves might bend in the grip of a black hole. The universe isn't just stranger than we imagine. It's stranger than we can imagine, and its temperature is the Rosetta Stone we're only beginning to decipher. The beauty of these mysteries isn't just in solving them, it's in how they reshape our questions. A century ago, we debated whether the universe had a beginning at all. Now we're probing the Planck era, where time and temperature lose all meaning. 50 years ago, black holes were mathematical curiosities. Today, we're measuring their heat signatures and pondering whether they're backdoors to other realities. Every leap in technology, from radio telescopes to neutrino detectors, peels back another layer of the cosmic thermal onion, revealing not just answers but new realms of wonder. What's next perhaps will catch the first unambiguous glimpse of Hawking radiation, confirming that even the darkest objects glow. Maybe we'll trace the thermal fingerprints of a collision with another universe, or detect the faint warmth left by a primordial black hole evaporating into the void. Or perhaps the biggest revelation will come from where we least expected: a lab experiment, a recalculation, a moment of insight that turns everything we thought we knew about heat and cold upside down. One thing's certain: the universe's temperature isn't a static backdrop. It's a dynamic, evolving narrative written in the rise and fall of energy across billions of years. And we're not just observers in this story. We're participants armed with curiosity and ever-sharpening tools, ready to read the next chapter as it unfolds in the cosmic dark. So keep looking up and keep wondering, because the next great thermal mystery might be hiding in plain sight, waiting for someone bold enough to ask the right question.